Hello. So after knowing the theory of the current mirror, this is the circuit of current mirror. Let's analyze its behavior using the SPICE simulator. So what I have done is I'm using this 5-volt DC voltage source, and this is the 5 volt coming, and I'm connecting this net physically here. So after that, I'm using this R1 is about 1 kilo ohm. So in fact, 5 volt divided by 1K, I'm going to set the 5 milliampere current into my circuit. So I reference that I would say, or it is also called as I input, I in, or I reference, whatever the name you prefer, is about 5 milliampere that I'm letting flow. And then this becomes your uh, collector current, that is IC1. Then this same current is also going in this direction and taking or being split into two equal parts, IB1, and then that is your IB2. Then you have this voltage drop here, which is VBE1. And because I would say this is my transistor Q1, and here is the collector, here is the base, and here is an emitter of this transistor. And I am making sure that the collector and the base of the transistor Q2, in fact, this is Q2 actually, they are shorted together, making Q2 as called as diode connected transistor. So when I say a diode connected transistor, I will have a simple PN junction where my behavior of the transistor would be a current flowing through. This is the input current of the transistor IB2. Let me use it and draw it in a very proper way. That is my IB2. And this is the VBE2. This is actually VB2, right? And this is how for the VCE2 values of the VC2. So I basically have, this is my Shockley diode model, right? Then the current flowing through this diode can be expressed by, let me remind the voltage ID. In this case, your the current IB2 is equal to IS VT over N VT, that is your VBE basically, minus 1. So VB2 is this voltage, and VT is the thermal voltage. IS is the reverse saturation current, which is ultra small. That's your diode model. So this basically transistor acts as a diode with collector and base shorted. Now VB2, and we can say that VBE2 is equal to VCE2, right? Because collector and base shorted, so base voltage comes right here, and that is the situation. This is for Q2. Okay, this is for transistor Q2. Now, if my transistors Q2 and Q1 are exactly same, so you see I have used the model from the manufacturer, which is 2N2222, 2N2222. So it's the same transistor. That means it will have same properties, same beta, same IC and VC specifications. With that said, I would say my input current I reference, which is basically a sink current. So this is coming into the circuit, right? So therefore, I would say, let me This is yeah. So I'm saying that this is sync part. Input side is the sync, and the output side is actually this is the current I out that is coming out of the transistor. But I can show the polarity in this way because there is this voltage source. So I will just correct the polarity here. Okay, so it's actually acting as a current source. So I out will be current source that is delivering current through the transistor Q1. And this I out will be equal to IC1. And I would say I out is approximately equal to I reference or I in 1, provided Q1 and Q2 are same, which are the case in this model. Now I have this voltage here that is VBE1, and this is the junction forward bias. Okay, this is the PN junction, and here in this part is also forward bias. And obviously your VCB is equal to 0 here because collector and base are shorted. So when you short the collector base junction, you basically have this acting as a diode connected transistor. How about this side? You have, let's say, collector of the transistor here. You have the base and you have the emitter, and exactly same configuration there. So now this is a forward bias diode, and if you need to decide what is the voltage at the collector. You know what is the voltage at the base. It is the positive voltage. So this is your NPN transistor. NPN transistor. So you need to bias the transistor Q1 in active region. Active region. So at the collector, there must be a small voltage that should be smaller than the voltage at the base, right? Or if you say that the voltage at the base is equal to voltage at the collector, so your VBC is equal to 0, just like in this case, in the transistor Q2. Then let me see how to bias this transistor, because your collector base junction should be forward bias. Right. So your collector base junction should also be forward biased to keep the transistor Q1 in active region, because the output characteristics of the transistor Q1 would be like this. You have this IC1, you have this VCE1 for the currents that is coming your IB, right? This is IB1. So there is this minimum voltage, which is this voltage actually, that is VCE1 minimum, right? So that must be maintained across, so that your applied voltage should be greater than this voltage to keep the transistor in active region. So that's why we are saying this junction is forward bias. So it means the voltage at the base should be greater than the voltage at the collector. That's it. So, and then that's how you will have this I out equal to I reference. So the first task now is to simulate the DC operating point of this circuit. For that, what we are going to do is click simulate, edit simulation command, click DC operating point. We have it already right here. So what I'll do, I will just right click this command, and I will enable this command right here. So let's say .op, that's it. And for a moment, I am not running the second type of analysis. I will disable it because that is the next part. So having done that, now we want to understand, click run. and our results are out. And here now we are all set to understand one by one all the points. So let's say your voltage here is 1 volt, which is like so voltage at the collector actually is greater than voltage at the base, you see, but I said you want it to be smaller than the voltage at the base, so that this junction is forward bias. So we'll see that how it goes. Now you have voltage at node 001. So you don't know what that node voltage is, but this is most likely this node, because that's the voltage, forward voltage drop of a diode. Then you have this supply voltage of 5 volt. Then look, the collector current IC of transistor Q1, which is of our interest, is about 4.2 milliampere, 4.27, and collector current of your transistor Q2, which is the input side of the circuit, is exactly also 4.26 milliampere. So approximately we are meeting this condition right here. We are meeting this condition because you see this voltage is about 1 volt. So the voltage, this diode actually, this collector base junction is reverse bias. So you are actually having the transistor Q1 in a linear mode of operation. Input junction forward bias, and output junction is I mean the base emitter junction is forward bias, collector base junction is reverse bias. So oh, that's actually your active region, right? Let me just be clear. The base emitter junction should be forward bias. Just a minute, let me be clear. Right, so since we have a 1 volt at the collector, we would say this junction is a reverse bias, but we want it to be forward bias, because if it is reverse bias, transistor is not saturated. It is acting in a linear mode of operation in this region. Saturation is this one, right? So next is your current through the R1, which is about 4.3 milliampere. So, but essentially we saw now that IC2 and IC1, they are more or less same. So this is how do that. Let's now do one thing. We'll drop this voltage to, we'll change this voltage right here to from 1 volt to, let's say, 0.5 volt. Okay, so that's now, and we'll re-simulate the behavior and we'll now see what output we have. So now you can see we have like 0.69 at this node, but current collector current is IC of Q1, that is 4.25, and then collector current of Q2 4.26, which is relatively same, but I have out this here is 0.5 volt, and here is like we have to get the 0.69, right? So now you see this diode is forward bias. The collector base junction is forward bias. So now you can say that that is saturated. Okay, uh, right here. So you need to bias it in the uh, make it saturated. So now with that said, next time we are now going to simulate the DC behavior of our circuit. We'll have the DC analysis. So let's do that. I will enable this analysis, that DC. And now what I'm doing is I am sweeping this voltage source V2. I have right click the spice syntax. That is my DC voltage source V2. I am using a linear sweep, starting value 0 and stop value 5 volt. Increment is 0.1 volt. So let me just click OK, and I will do that. Okay, so I have already two curves that is I am plotting. The first one is transistor current through the resistor R1. That is my reference current, which is about, let me just get this here, which is about 4.3 milliampere. Okay, so let us zoom that portion and we'll see how much is the current that we have. Okay, let us zoom to fit, and then we'll zoom this area. So it's about 4.3 milliampere right here. And now have a look at our green curve, which is about, which is our current through the output transistor, that is Q1, which is this one, right? And we see now this is how it is increasing initially. This is the voltage across it. And exactly at about 100 millivolt, if we zoom this portion out, about 120 millivolt voltage across the transistor Q1, it starts and this junction is forward bias, the collector base junction, and both the junctions being forward bias, it is saturated. We don't want to use it as an amplifier. We want the transistors to be saturated, right? Output transistor. So that's it. So it provides us a constant current, and it acts as a constant current source, as you can see from the green curve, irrespective of the load conditions. Okay, so this is how we manage to build a constant current source. Then you can connect the load here, and that will be the current that will be delivered. In case if I want to, let's say, plot the IC1, here I have plot IC2. Actually, this is the red curve. And if you compare the red with the green, let us zoom. Yeah, so they are more or less same. IC2 and IC1 of the transistor, they are same. Now, if you want to plot the voltage VBE, let's have a add plot pane, and this is the voltage at the collector. So as soon as your current source starts working, as soon as you drop the voltage of about 120 millivolt across transistor Q1 across its collector to emitter, you have the constant current and the constant voltage of about 694 millivolt. You can also use it as a reference voltage source. And this voltage is the same. You can then plot various currents and the voltages. So that's it. Now let us see the voltage here is 694. And what is the voltage here? So we see that. So voltage here, basically we are sweeping. That is the voltage we are sweeping. So that's it. So you see, you have this, this is how you actually can simulate, design the current source or current mirror actually, which is subsequently provides you a current source. Here the transistor value you can see for this pickup transistor, your transistor beta is 200 beta factor, that is DC current gain. So accordingly do your calculations how you want to design for a specific current. Now, next job is to, the green is the output current. If you zoom in, let's remove the other one, or maybe in another, add plot pane and right click here and add the trace about ICQ1, which is my output current. And if I zoom this portion, so output resistance for which the theory equations has been given in our previous model. Now you see that there is almost constant, right? But this can also further be improved. If you take a slope of this, you will see that the right. So once you make the collector emitter voltage of the transistor Q1 fall below 120 millivolt, the current, it is no longer acting as a current source. The current mirror will not behave properly. And they take a slope of this green line, you will get the output resistance or output conductance also. Okay, so that's all for this class.